Okay. Okay. Good morning. Good morning, my dear students. Good morning. Good morning to all of you. Nice to meet you. Good morning. Nice. Okay. Good. For today, what I am going to discuss with you, I am going to discuss with you today this one. I am going to discuss with you today advantages and disadvantages of finite method. Advantages means merits. Okay. And disadvantages, demerits, or limitations of containment method. You can say any manner. First, we are going to see the advantages. You get common sense. You can tell in your own. Sir, what are the advantages? First, let me to tell in my own, and then we will go through the points as per the textbook. Okay. First advantage. What for you are doing containment method? What for you are using it? For field analysis. Okay. Field variable. The word field variable is very important. The field variable may be anything. Okay. Most of you do stress analysis. Okay. We say structural engineers, we civil engineers, we do stress analysis. So ours is our field variable is stress. Okay. So that's what. Actually, this finite element method applicable to any field. Okay. It is applicable to any field problem. You can say any field problem. Sir, what's our field problem you are saying? Stress analysis is a field problem. We civil engineers, we structural engineers most of the times deal with it. And then you take mechanical engineers, they also deal with stress analysis problem, no doubt. Okay, like us. In addition, they also do heat transfer. Okay, heat transfer is thermodynamics. No, there also that also a field variable. Heat transfer is a field variable. Okay, thermodynamics is a field variable. There they use. Okay, FEM is applicable to even a field variable like that also, heat transfer also. You take electrical engineers, magnetic field. They deal with the magnetic field. There's a field variable, magnetic intensity field variable involved. They can do this finite method to analyze such field variable also. Okay, and so on. Right? So the finite method, main advantage of finite, okay, and advantage, the first advantage I am telling you, finite method is applicable to any field problems. Okay, like for example, stress analysis, heat transfer, magnetic field kind of problem, any problem, etc., etc. Okay, that is the first advantage. I am coming to the second advantage. The second advantage is you have to start with material property, shape, geometry. Okay, there is no restriction to geometry of the body to be analyzed. There is no restriction. Body of any shape, any dimension can be analyzed. Body of any shape, any dimension can be analyzed. There is no geometrical restriction. Okay, that is the another main advantage. Okay, second advantage of finite method. Third, first I talked about its application advantage, and then its geometry advantage. Third, I am going to boundary condition. Okay, there is no restriction to boundary condition of the body. Okay, to be analyzed. There is no restriction for boundary condition. The body, it means what? In the body, it can be supported at any place, any part, any portion of the body can be supported. The body to be analyzed, any portion of the body can be supported. While any portion of the load can be distributed force or concentrated force can be applied at any other portion of the body. We don't have any such restriction. No, load should act this way, that way. No, it can distributed load or concentrated or whatever it is. It can act anywhere on the body. Similarly, the body can be supported at any portion. Okay, that can be analyzed by finite method. So this is a signed third advantage. Okay, and then fourth, okay, I might have forgotten. Okay, no problem. While referring the notes, okay, just let me to refer the notes. I will tell you. Fourth one, yeah, that's what. Material property. Okay, there is no restriction to material property, right? It is not necessary that the body to be analyzed should be isotropic material. No, there is no restriction to material property. Okay, the material property vary from one element to another element. One element, one property, in another element, you can use another material property. Okay, so the material property can otherwise finite elements of different material property can be combined and analyzed. Okay, it can be used. Even the material property can be varied within the element also. That you have to remember. Okay. So I talked about its application, and then geometry, boundary condition, material property, because you will be feeding. While working the package, you will be going by these steps: geometry, and then boundary conditions, material property will be assigning, Poisson's ratio value and smallest value will be feeding. Okay, so in that order you will remember to tell the points. Okay, so these are the main four or five advantages I have told you. What else is there? Just let me to refer. Okay, that's what. Okay, different elements can be combined and studied. That's what the fifth one says. Okay, right. Actually, finite element structure, finite element model. No, that is called a finite element structure. Can resembles the actual physical structure. Okay, it's capable of resembling the actual physical structure. That also added as one of the point in the advantages. And then the lastly, you can improve its approximate method. No, the approximation can be improved by grading the mesh of the finite element. Okay, grading the element means where the field variable is more gradient or more having more how to say concentration. Okay, those places you can do proper grading. Okay, grading means more resolution. Where more resolution required, where more concentration of field variable is there, there you can go for finer grading. Okay, finer meshes. That's also possible in that where more accuracy is required. Already told you this point. Where more accuracy is required, where more accuracy is required, where there is a field variable concentration is there or more resolution is required, there you can go for higher grading. Higher grading means finer grading of the elements. Okay, so as to achieve accuracy there. So these are the I told you these are the advantages I took from some book. I referred to several books. I told you no, because these are the advantages given in C.S. Krishnamurthy textbook. I also parallelly referred this C.S. Abalan Desai. In that, the point is given in different way. Those points also I have included as 3A, 4A in my notes. Okay, I will discuss with that. So far, I have told you some. You can easily remember the advantages. Okay, because without I am telling how to remember the advantages. Just now I told you. And then what is the disadvantages, sir? What is the limitation of finite element method? What is the demerits of finite element method? If you ask me, we are not supposed to say disadvantage. Okay, disadvantage or limitation of finite element method is that actually certain complex phenomenon cannot be represented properly in it. For example, the fracture and cracking of material, cracking or fracture of material can be a certain behavior cannot be complex behavior, cannot be modeled properly with the finite element method. That is the limitation. Example, this cracking and fracture of materials, and then debonding of materials. Okay, when two materials are bonded together, the debonding that we encounter mainly in composite structure. Okay, if you suppose you take FRP composites, when we load a FRP component, they're going to be delamination because the FRP is laminated. No, the delamination kind of behavior cannot be modeled properly. Okay, there's such on the certain seepage problem, unconfined seepage problem cannot be properly modeled. Certain few such limitations are there in finite element method, no doubt. Only 2 points if you write in the limitation more than sufficient. These are the main 2 points. The another point is the expensive. This method is expensive. Expensive means you require a computer and programming you have to write. Now, package is available. You have to purchase a package if you want to analyze. Suppose you are at home, you want to do finite element method analysis. What to do? You require a laptop. You have to buy it. Okay, and you have to purchase a finite element software. So that is a cost effective. Okay, prohibitive. Cost involved is high. Okay, so expensive. The finite element method analysis is expensive. Actually, this book where these theories were written 30 years back. 30 years back, obviously, the computer was the costliest one. Okay, and now it is affordable to you. Everybody is holding a laptop with you. But you take 30 years back. 30 years back, most of the, I will just tell you, the topmost scale up, many professors in colleges were getting only 4,000 rupees or 3,000 rupees salary. Within 4,000 rupees, their total emolument. Okay. Some 30 years back, you see a senior most professor in a government engineering college. Okay. Topmost scale up pay, even including IAS officers, collectors. Their salary, professor salary and all same. Scientists, professors, collector, all are all India competitive job, and their scale up pay also is same. The same. Okay. They were getting only total emolument 4,000 around. That time the price of a computer was 1.5 lakhs, 2 lakhs. Na? Think about it. It was too expensive. If they want to work with the finite method, they have to purchase a computer for 1.5 lakhs those days, 30 years back. Okay, that this book textbooks were written that time. There in the disordered limitations they were mentioned. It is a cost expensive doing analysis with the finite method, because you require a computer and you have to purchase a software. That time the program was the Fortran. Okay, punching system and all. Nowadays, nice packages have come. Okay, that was the main disadvantage involved. Okay, there are some other disadvantages. I will project my notes and discuss with you. Okay, so these points, if you write whatever point I just now I discussed with you, if you write during exam, you are asked when you are asked to discuss advantages and limitations or disadvantages of finite method, more than sufficient. Okay, whatever I told you. What are the other points involved? Who is Dhanlakshmi? Okay, right. Right, I will discuss with you. Okay. See here, advantages of finite element method. FEA has advantages over most other numerical analysis. Listen, FEA has advantages over most other numerical analysis. Please see here, FEA also one of the numerical analysis procedure. Okay. There are other numerical analysis procedure. In the very beginning, I told you. Right. For the first advantage, FEA is applicable to any field problem. I just now I told you. Heat transfer, stress analysis, magnetic fields, and so on. Okay. No doubt. Just now I told you. Okay. Second advantage, there is no geometric restriction. The body or region analyzed may have any shape. Okay. And dimensions. Okay. Right. Next to third point. Boundary conditions and loading are not restricted. Not only boundary condition, loading I forgot to tell you while discussing. Okay. Boundary conditions and loading are not restricted. For example, in stress analysis, any portion of a body may be supported, while distributed or concentrated forces may be applied to any other portion. Okay, I told you no, the same point, right? The fourth point, material properties are not restricted to isotropy. Okay, and may change from one element to another, or even within an element. Okay, this much advantage involved. Fifth advantage is components that have different behaviors and different mathematical descriptions can be combined. Okay, thus a finite model might contain a bar, beam, plate, cable, and friction elements. So many. Okay, it may be bar element, line element, link element, or beam element, plate element, cable element, or friction element. In any finite element model of a structure will be having all these elements. Okay, that is elements of different properties can be combined so as to resemble the original physical structure. Okay, that's what the fifth point says. Sixth point, an FEA structure closely resembles the actual body or region to be analyzed. No doubt. Okay. Now, okay. Next, seventh point, the approximation is easily improved. It's approximate method. No, it can be easily improved by grading the mesh. Grading the mesh means what? Finer grading. Okay, grading. What is that? In sand, we say grading. No, finer size, coarse size sand grading. That word. No, we used to know. That's what. The approximation is easily improved by grading the mesh. Grading the mesh means you can go for finer mesh. Okay, instead of going for coarse mesh, bigger mesh. Okay, finer mesh you have to go where more resolution is required. There you have to go for finer mesh, so that more elements appear where field gradients are high. Where field gradients are high or more resolution is required. Where field gradients are high or more resolution is required. That's what. For example, you take a continuous beam. Okay, in a continuous beam, I don't require resolution. Where more resolution is required at a mid-span, where the sagging bending moment is high. At a support, okay, at support where the sagging bending moment is high. There more resolution is required for me. because the stress concentration will be more. Okay, I have to focus there more. Those are the regions where more resolution required. There you have to go for finer grading. Okay, finer measures. That's what. Where more accuracy is required, you have to go for finer measures. So the approximation is easily improved by grading the mesh so that more elements appear where field gradients are high and more resolution is required. That's what I told you just now. And then eighth point I will finish, then I will come to that one. Eighth point. So finally, the eighth point states the systematic generality. Okay, the systematic generality of the finite element procedure makes it a powerful and versatile tool for a wide range of problems. Okay, as a result, flexible general purpose computer programs packages can be constructed. That's what. Because in this method, the main advantage of this method is systematic generality of the finite element method. So it can be nicely written. The steps procedure involved can be written in a systematic manner. Okay, so it is programmable, right? Okay, the systematic generality of the finite element procedure makes it a powerful and versatile tool for a wide range of problem. Means it's also programmable. Okay, as a result, flexible general purpose computer programs packages can be constructed. There are plenty of nowadays plenty of finite element software available. You are aware of only that ANSYS, Abacus, and other maybe StatPro or ETAB or something. Okay, these are the finite element packages you may aware. Okay, apart from that, there are several finite element packages are available. Okay, even earlier we had okay. Right. I forgot that. It's okay, no problem. Next one, I will tell you. There are other points I took from Abhilant Desai. Okay, these are the points of C.S. Krishnamurthy I discussed with you. So he has given in this point I took from some other book, maybe it be from Abhilant Desai or R.D. Cook. I don't remember. But 3A, I have written it as 3A. It is similar to that of third point. What is third point? Boundary conditions and loadings are not restricted. No, in the third point it resembles. That's why I written 3A. Okay, that's why I have written 3A here. One prescribes the conditions, okay, boundary condition, after obtaining the algebraic equations for the assemblage, no doubt. Since the boundary conditions do not enter into the equations for the individual finite elements, one can use the same field variable models for both internal and boundary elements, okay. Moreover, the field variable models need not be changed when the boundary conditions change. I will repeat, I will read it once again. I will explain what it says. See, this is another additional point, advantage, okay. One prescribes the condition, okay, that is boundary condition. When we apply, impose the boundary condition, after obtaining global stiffness matrix, no, that is global equation, after obtaining the algebraic equations for the assemblage, after assembling them, okay, after assembling them, you recall your basic steps in finite element method. Later we apply the boundary condition, okay. That's why, since the boundary condition do not enter into the equations for the individual finite elements, okay. So the boundary condition need not be incorporated into the individual finite element properties. That's what it says. One can use the same field variable models. You have developed a model. One can use the same field variable models for both internal and boundary elements. Okay, the same finite element can be used for internal element in the body as well as even boundary element, elements which are there at the boundaries. Okay, same element can be used. That's what. Moreover, the field variable models need not be changed when the boundary condition change. When the boundary condition change, you need not change the element. The model can be like that. Only the boundary condition you can change it. Okay. Why? How? You will remove the boundary condition from that particular element. Suppose the bodies you deal with a body supported somewhere. For example, you deal with a beam supported at the end. Okay, you modeled it. Suppose one end I am bringing inside the support. The support I am moving. The boundary condition I am moving. Okay, I am making it a one side overhanging beam. I need not change the entire finite element model of the beam. I can keep it. Only by boundary condition to the last element, I am removing it. I am removing the support and introducing that support at boundary condition at some other element. Okay, that's what. The same, for that I need not again do once again model right from the beginning, no need. Only okay, that is the main advantage. You used to play some the game, no, that varying cap, glass and all, some animation you will do, no, similar to that, finite element, okay, software. Once you developed the model, na, in that, suppose you load you are applying, okay, concentrated load you are applying on certain particular element. That way the beam is loaded. You are analyzing it. You want to change the load. In the already you have modeled the beam. You can keep it as it is, and only you have to remove the load, previous load from the respective element, and you have to apply the load, the new system of load at elements, required elements. Okay, and you can carry out the simulation, the analysis. Can you able to understand what I am trying to say here? That's what. So that is the beauty of this software. Okay. So that's what. Every time you need not do right from the beginning once again the model, right? If you want to, once the model created, you can keep on changing. For example, I am doing a, okay, I don't want to, yeah, I am doing a wrapped, okay, wrapped beam. I modeled it in my finite element software. Okay, it is of a glass fiber. Now I want to change it to carbon fiber. Again, I need not sit and do a model right from the beginning. Already my model is there in the computer. Only thing is I have to change the property of the mesh. That's all. That wrapped mesh, that wrapping, no, that wrapping material. Wrapping material I have done with some element, finite element in the model. No, only thing is I have already assigned a material property. The glass fiber material property I assigned. If I change the material property of a carbon fiber there, it is a carbon wrapped fiber. That's all, beam. Okay, so only what such changes possible. Okay, hope you would have got it right. Very good. Next time we'll go to the another discussion. 4a. The finite element readily accounts for non-homogeneity. Please remember, the finite element readily accounts for non-homogeneity. How? The material need not be homogeneous. The material need not to be analyzed need not be even isotropic. Even non-homogeneity can be accounts. Okay, by using different elements. That's what it says. Different elements by simple tactic of assigning. I will have some water. Okay, homogeneity by simple tactic of assigning different properties of different elements. Oh, that's what simple tactics. You can use elements of different properties. Okay, this way the non-homogeneity can be okay. Actually, here, yeah, can be accounted. Not only non-homogeneity, also account for anisotropic. Also accounts for anisotropic, non-linear. So the material can be not be linear behavior, even non-linear behavior, hysteretic, even time-dependent or temperature-dependent material behavior can be studied. Okay, sir, what is a time-dependent behavior, sir, or what is a temperature-dependent behavior, sir? That the question arises, no. Okay, if I discuss, it will go lengthy. So no problem. Time-dependent behavior, for example, elastomeric bearing. You take that rubber. You are dealing with the behavior of rubber. You are loading it. Okay, immediately there are going to be a deformation in it. Not only rubber. For example, I'm telling, because usually you can visualize. That's why I'm telling a rubber. Even it is happening in our concrete also, beam also, steel also, steel material beam also, it is there. Okay, what happens? It deforms. Suppose if you leave it under a sustained load for a long time, there are going to be further deformation in it with respect to time. That is called time-dependent behavior. That is the best example is creep behavior of any material. Creep behavior of any material is nothing but time-dependent behavior. Okay, can you able to understand what is creep? C-R-E-E-P, creep. Creep means if you keep any material under sustained load or sustained stress, with respect to time, there are going to be deformation in it. Okay, that phenomenon is called a creep. Okay, that is the one. And then temperature dependent behavior. Of course, temperature dependent behavior. You take a rubber mounts for vibration control. We put rubber mounts in machineries. Industrial machineries are there, no, that will cause us vibration. that the vibration will come to the floor, okay, due to which the concrete structure will be affected if the vibration is continuous for a long time, okay. Or if the vibration come to floor, you will be standing, okay, near the machine to operate it. You will feel uncomfortable. That is why most of the machineries are, industrial machineries are mounted on rubber mounts, okay, rubber mounts called isolator, vibration isolator, okay. They are subjected to how to say, vibration for a long time, no. With respect to time, the rubber will be get heated. That will change its behavior, okay. That is called temperature dependent material behavior. Okay, just for example, I told you. Okay, forget about not itself. We are an M.Tech student. That's why I'm telling some all this thing. Okay, I will read it once again. The finite element readily accounts for non-homogeneity by simple tactics of assigning different properties to different elements. Okay, also accounts for anisotropic, nonlinear, hysteretic, time-dependent, or temperature-dependent material behavior. Everything. Wow! By employing finite elements of different material property and different behavior. Okay. We can account all these things, okay, all this behavior of material, hysteretic behavior of material, nonlinear behavior of material, anisotropic behavior, non-homogeneous behavior, time-dependent behavior, temperature-dependent behavior, all behavior can be simulated, okay, can be modeled, right? That's all. Advantages are over, okay. Nice points we have discussed. Whatever points you remember, you can write during exam. Read it, try to understand, and try to write in your own words. So, okay, it's that's what. Next, I am going to disadvantage, limitations. Just now I told you, no, without referring the notes, I told you. Okay, I will tell you. Read it here. One limitation of FEM is that a few complex phenomena are not accommodated adequately by the method. That's what. One limitation of FEM is that a few complex phenomena are not accommodated adequately by the method. Okay. Example: cracking and fracture behavior, contact problems. Okay. That's what the notes is cut to here. Okay, it's here. Okay, cracking and fracture behavior, contact problems, bond failure of composite material. Bond failure of composite material. I told you, for example, FRP wrapped material, when you load it, there are going to be failure mode. The failure mode will be delamination of that wrapped material. That is somewhat difficult. That is, it's a bond failure. Best example for bond failure of composite material. That cannot be properly modeled. That's what. Propagation or transient problems, unconfined seepage problems, etc. Okay, these are the disadvantage, limitations of finite element method, and the cost involved in the solution of the problem. Cost of analysis by FEA may be prohibitive, expensive, highly high. Okay, because I told you the reason. I already explained nicely that one. Okay, in detail I explained. What are the other limitations? There are 3 more points I have written. Okay, these 2 points are important. What are the, you can easily remember, what are the other 3 more problems, points I have written? Stress values vary by 25% from fine mesh to average mesh analysis. Okay, that's what. That is another limitation, disadvantage of this one. Stress values may vary by 25% from fine mesh to, that is fine mesh analysis to average mesh analysis. That you can include it as a disadvantage. Okay, but the 4th one. There are other trouble spots such as I forgot to tell you. There are other trouble spots such as aspect ratio. While providing the elements, you have to be very careful. Certain the aspect ratio, certain value should not be exceeded. It should not be too narrow. This one. What is aspect ratio? Ratio of larger to smaller dimension of a element. Ratio of larger. In other words, the element should not be slender one. Okay. Ratio of larger to smaller dimension of the elements. There are other trouble spots such as aspect ratio, which may affect the final results. Okay. However, these are easier to guard against than the problem of the proper mesh size and distribution. It's okay. So you have to be careful with the aspect ratio. It should not be too large. It means the material should not be slender one. The element should not be slender one. Okay. You have to take some care. Sometimes the aspect ratio will affect the solution. Okay, while choosing the element, you have to be a little careful of that one. That's what it says. Another disadvantage. The 5th disadvantage also I have written, right? Limitation I have written. Another problem lies in the very nature of FEM, namely the approximations used in the development of the element stiffness. Okay, that's what. Another approximation used in the development of the element stiffness matrix stiffness. Actually, the element stiffness matrix we develop approximate manner. We write a shape function and then strain displacement model, the strain displacement matrix, and then we obtain the element stiffness matrix and all. In that, there are some approximations involved. Okay, that's what it says. The problem lies in the very nature of FEM, namely the approximation used in the development of the element stiffness. No element can be all things to do all people. Remember, keep it in mind. No element can be all things to all people, and no element can represent all possible behavior patterns equal well. Compensation in one aspect causes distribution of another. We should know what a particular element is capable of and must not expect more from it. It's okay. This point is not important, just for your information only it is given. Okay, just for information. You cannot take it granted everything. There are some restrictions in element. Okay, that's what this way they conclude the limitations. Okay, we should know what a particular element is capable of and must not expect more from it. That's what it says. Okay, like that the limitation is concluded. So we have seen advantages and disadvantages of finite method. With this I will stop. I will finish the class with this one. Okay, this one. Okay. Next unit 1 is almost over. Okay, I completed a unit 1. Next I am coming to unit 2 of your syllabus. Okay, element properties. We are going to see in the second unit fully element properties. Okay, here I am going to do a lot of derivation, only derivative part. No working problem. It's not problem oriented. The second unit is derivative oriented. Okay, full derivation we are going to do. We are going to derive. We are going to develop shape functions. That's what we are going for. Several standard elements we are going to learn it. Okay, let us see. Typical finite elements. Typical finite element, if you see, for plane stress strain and axis symmetric analysis, listen here, for stress strain analysis, that which is stress strain, plane stress strain analysis. Okay, two-dimensional. Plane stress strain analysis means some plate problem and all, two-dimensional. And axis symmetric analysis, axis symmetry, you take a rotating cylinder or rotating sphere. Okay, or rotation of a rigid body about an axis. Okay, suppose a body rotating with respect to its own axis, especially it is given axis symmetric analysis, cylinders, sphere. Okay, they are axis symmetric problem, right? For such analysis, we use mostly three-noded triangle. If you do linear analysis, we are going for three-noded triangle. If you want non-linear analysis, you have to go for six-noded triangle. Please remember here, only three-noded, it's a linear element. In between, if I introduce nodes, I am making it as non-linear. Okay, the element will behave in a non-linear manner. Six-noded triangle. Okay, in that case, we call it as six-noded triangle. Please remember, more node to account non-linearity in it. Remember. And a four-noded quadrilateral element. So like that. Okay, not a rectangular, some shape like this. We call it as quadrilateral element. Four-noded, it's a linear element. Okay, if I want to make it non-linear, what to do? I have to introduce apart from in addition to corner nodes, edge node. At the center, I have to introduce edge nodes like that. Okay, in line with the corner nodes. Okay. Now it is called eight-noded curved element. Okay, this is for non-linear, to analyze non-linear problem. And then four-noded rectangle. This is for plate bending and shells. There are plate bending and shell problem. Okay, you don't have theory of plates and shells in a separate subject. There you will be studying about plate bending and shells. In that, four-noded rectangle element. Okay, four-noded rectangle element. If I say four-noded, it is a linear element. For to study linear behavior of that body, we use this kind of element. Four-noded quadrilateral element. This is also a linear element, right? And then eight-noded curved element, same thing. Here you are using similar element. I have drawn in different map fashion. Okay, it's eight-noded curved element. Once you, apart from corner node, if you introduce into edge nodes, it is these elements are used to study non-linear behavior. They are non-linear element. Okay, how you will see while developing shape function, you will understand. and then three-dimensional stress analysis. To do that, we use this kind of four-noded. These are the most widely used element. That's what it is. Typical finite elements, most widely used elements. Okay. For three-dimensional stress analysis, four-noded tetrahedral element. How it looks? See here, four-noded tetrahedra element. There are four phases in it. Called it tetrahedra element. Okay. It's four-noded. It's a linear element. Eight-noded hexahedral element. Hexahedron element. Okay. There are six phases in it. That's why hexahedral element. There are four phases in it, tetrahedral element. And 20-noded curved element. In the same element, if you introduce edge node, okay, additional edge nodes like this. This kind of elements are used for nonlinear analysis. 20-noded curved solids. Okay. Okay, that's all. Next class, I am going to start this one. The topic is not available visible here. Displacement model. How to develop a displacement model, shape function and all. We are going to learn. Okay. This I will continue in the next class. Good. Okay. I will stop discussing. I will just record your names. Right. Just I will record your names. Okay. Yeah, M.Tech always full present. All of you are attending. Okay. Good. Right. I will do one thing. I will stop recording. Then we will, if you want to have any talk, we can have a talk.